misinformation question having to do with data compression. And then finally, we discussed arithmetic coding, which is a really nice way to code. We know that if x is drawn according to f of x, then the quantile associated with the random outcome x is uniform 0, 1. I'll call it U. So you get a uniform distribution. So this is ideal for, let's say, if you wanted to generate a sample function from a stochastic process, just calculate f of x for the infinite sequences for that stochastic process. You want to order them somehow, because f of x has to do with the probability the infinite sequence x is less than or equal to too little infinite sequence x. And then you would just use f inverse of u. So you look up in a table of random numbers or generate random numbers, and when you calculate f inverse of u, you get a sample function from a process, and it has the right probability distribution. Furthermore, by reversing the procedure, you get maximal data compression. You take a stochastic process x, remember x is like this real number corresponding to put a decimal point in front of the infinite string. And you map the sequences from the stochastic process into the unit interval in such a manner that you get a uniform distribution here, which means when you read out the bits, say, that it's a Bernoulli half process. So you get maximal compression. By the way, how many bits of x correspond to k bits of u? Well, with k bits of u, you now know u to accuracy 2 to the minus k, and that allows you to determine the atoms of x to that accuracy. And the n symbols of x have probability by the AEP of 2 to the minus nh for most of the sequences. So k symbols of u will give you nh symbols of x. So you're getting a compression from n symbols down to essentially nh symbols of u, and so on. So in fact, this is a very good way to do the data compression. Say I wanted to do the data compression on a piece of on an image. Well, then I just use my best predictor. It has p hat of the next gray level, given everything I've seen before. And I encode, I find f of x, I encode, do data compression with respect to p hat of x, and the associated f hat of x. And I get optimal data compression if p hat is true, But if p hat isn't true, if indeed I designed for p hat, that is q is p hat, when p is true, then it costs me the distance of my predictor from the true distribution. So no harm is done, because every predictor is pretty good on images, pretty good on music, pretty good on text. And how this is the cost of how bad it is. That is dp p hat. All right. Today, we do channel capacity. It won't be on the midterm. And it's chapter 7. And then later, not today, but towards the end, we'll do Gaussian channel. Channel capacity, the most famous result theory. And that's chapter 9. Chapter 8, some maximum entropy, will do that in beginning of next quarter. Okay. All right, first of all, capacity is equal. This is the sort of thing we want to make precise as a statement and then give a precise proof. The capacity is equal to the log of the number of distinguishable inputs. So, for example, we could have a channel in which we put in X from some finite alphabet. We see a random result Y, and we wonder how many distinguishable X's there are as observed by Y. And as a particular example, we'll look at this one, P, 1 minus P, 1 minus P. It's called a binary symmetric channel. X is 1 or 0. And if you see, if I send a 1, there's a probability of error P. Let P be, say, a tenth. Well, that means that when I see a 1 here, even if I'm probably wrong a tenth of the time. So the inputs are not distinguishable. Well, unless you consider being wrong a tenth of the time, meaning you can see it. And yet, if we repeat uses of this channel, all of a sudden things become asymptotically distinguishable, and we can state a precise theorem. I want to draw a connection with data compression. Recall data compression. Two to the h equals equals number of letters in alphabet. Well, what do I mean? I don't know. We had an original alphabet X, and then because of data compression, we can compress these M symbols and X to 2 to the H symbols here. So that's a vague statement, but we've made it precise. Well, similarly, 2 to the C equals number of distinguishable inputs. So 2 to the H is the effective alphabet size of a random source, and 2 to the C will be the effective size of the input alphabet. By the way, if P is 1/10, we'll find out that the alphabet size is half a bit. So it takes 2 transmissions to get up even to 1 binary symbol that's distinguishable. All right, so we have a definition of a discrete memoryless channel. I'm not going to write it out. DMC. It consists of an input alphabet, an output alphabet, and a probability of y given x. So P of y given x is greater than or equal to 0, and sums to 1 for all y, for each y. And the binary symmetric channel is an example of that. And the nth extension would consist of xn, yn, p of yn given xn, and with one extra provision. The distribution of yi given all the other x's just depends on the current x. So this is equal to the product of p of yi given xi from I equals 1 to n. This is what makes it a memoryless channel. So really what is important here is not the discreteness of the channel, that is finite alphabet in and out. When we get to the Gaussian, you'll see that doesn't matter. But what really matters is that it's a memoryless channel, and it chops up what's going on. So every time you send an X, what happens to it is independent of what's happened to your other transmissions. And that's really allows us to invoke the law of